Hello everyone. Today we're going to take a look at Unit 1, Lesson 5, Setting Up Word Problems. So we're going to take what we've learned about solving linear systems with our two algebraic methods in order to solve word problems. So today really all we're going to do is actually set up the word problem so that we've created these linear systems, and then the next few lessons we'll take a look at actually solving them using substitution and elimination. So we'll get started with our first example. The difference between two numbers is 63. When the larger is subtracted from twice the smaller, the result is 49. Find the numbers. So we'll try to break down these word problems so that we can figure out what each sentence is saying in terms of an equation. We'll always have to first identify what variables we're going to use and then communicate what those variables represent. So it says the difference between two numbers is 63. So when the larger is subtracted from twice the smaller. So it looks like our variables in this case, we have two things that are unknown. We have a larger number and we have a smaller number. So we are going to write a sentence just to communicate that we need variables to represent that. So we're going to say let x represent the smaller number and we'll let y represent the larger number. And we don't have to use x and y. You could use L and S for large and small. You could use A and B. It really doesn't matter. Often what we'll do is we will pick variables that are the first letter of whatever the description is of that variable. So it's kind of clear to see what that variable represents, and we'll do that in the next example. So we have x is our smaller number, so that's right out of the word problem, and y is our larger number. Okay, so we're going to look at each sentence and see if we can come up with an equation for those. So the difference between two numbers is 63. Okay, so the difference, hopefully we see that, I'm going to use a different color. So difference in math means subtract. All right, and between two numbers is, when we see the word is, we should be thinking means equal. Okay, so if it's the difference between two numbers, well, if the result of that is 63, that's a positive number. So hopefully we can see here that we need to do our larger number minus our smaller number in order to get a positive number. So our larger number is y, our smaller number is x, and that's saying it's going to be equal to or is 63. Okay, so that's my equation 1. So that's half of my linear system. Let's see if we can come up with a second equation for this linear system. So it says when the larger number is subtracted from twice the smaller. Okay, when the larger number is subtracted from twice the smaller. So twice the smaller would be 2x, and then the larger number is subtracted from that, so minus y. The result is 49. Okay, so that's my equation 2. So here now, we've set up our equations. So that's really, sometimes with a problem, the most difficult part. Once we're comfortable with elimination and substitution, then when we move on to word problems, we just need to make sure that we're actually setting them up correctly so then we can carry out that process. So that's the only thing we're going to do today is set up the word problems. So then tomorrow we will solve using substitution or elimination. And again, tomorrow we'll go through and look at the problems and say, okay, which method makes the most sense for this system based on kind of what we talked about in the previous day's lesson in terms of how they're set up. So let's take a look at that next example. So the school pop machine contained 71 coins in quarters and loonies. The value of the coins was $30.50. How many loonies were there? So again, we have to look through the word problem and see, okay, what are the things that are unknown in this word problem? And they're talking about coins. In particular, they're talking about quarters and loonies. So we're going to give a variable to each of those things. So in this case, let's let the first letter of each of those types of coin represent that coin. So we'll let Q represent quarters, and we'll let L represent loonies. And when we use an L for a variable in math, you'll usually see it written as a cursive L, just because if we write it as a traditional L, it looks more like a number 1. So if we write it as a cursive L, it's less confusing. Okay, so we'll try to make some equations out of each of these sentences now. It says that the school pop machine contained 71 coins in quarters and loonies. Okay, so the sum of however many quarters and loonies we have is 71. So we could hopefully see that this is addition. So we'll write an equation for the number of coins in the machine. Okay, so when we add our quarters plus our loonies, there should be 71 coins. That's my equation 1. Okay, the next equation says the value of coins. So we need an equation to represent our value of coins. The value of coins was $30.50. Well, again, so we're adding together our quarters and our loonies, but we need to include on that the value of each of those. So to represent the value, say if I had 5 quarters, I would need to multiply it by how much a quarter is worth. So a quarter is worth 25 cents. So 25 cents times however many quarters I have will tell you how much money in quarters I have. The same is true for a loonie. A loonie is worth $1. Okay, so we'd have to do $1 times however many loonies I have. And the addition of those two things should equal $30.50. And that would be your equation 2. Okay, if we take a look at this next example, let's choose our variables together and then pause the video and see if you can set up the equations. So it says twice Andy's age is increased by 3 times Ashley's age is 93. Okay, 5 times Andy's age decreased by 4 times Ashley's age is 37. How old will Andy be 10 years from now? All right, so it looks like we're trying to figure out a couple things here. It's asking us about Andy's age in 10 years, but it seems the unknown throughout this question is Andy's age and Ashley's age. So let's write some variables to represent those two things. So let's let we're going to use a subscript here so you can see what that looks like. Let's let Andy's age, because both their names start with an A, so we'll put the second letter of their name as a subscript. So I'm going to write that this is a subscript. When you have that little letter to the bottom right of a like just a regular size letter. So let AN represent Andy's age. And then we will let A with a subscript S represent Ashley's age. Okay. Now take a look at those sentences and see if you can break them down into 2 equations for a linear system. Pause the video now and give that a try. Okay, there is the solution to represent Andy and Ashley's age, and then once again, tomorrow we'll take a look at actually using substitution or elimination to solve these. Okay, our last couple problems for today are very specific type of linear system word problems. And these are called mixture problems. It's where you're essentially mixing 2 types of something to result in something else. So with these mixture problems, it's a lot of kind of percentage information or time information. So it's usually beneficial to set up a chart. So just to make that point, we're going to try to set up a chart for mixture problems. All right, so let's read through these and try to break down what our variables are like we have in the previous examples. So it says one type of trail mix has 20% chocolate pieces by mass. A second type has 5% chocolate pieces. What mass of each type needs to be mixed to make 950 grams that will have 10% chocolate pieces? So again, with these percentages, it seems like we're dealing with a lot of different numbers than we were in previous questions. But it's important to recognize what still is the unknown in this case first. That will make setting up the problem a lot easier. Okay, so the question is saying to us what mass of each type. So well, we have two types that we're working with here. We have trail mix that's 20% chocolate pieces, and we have trail mix that's 5% chocolate pieces. Those are the two types of chocolate we're dealing with. So first off, those are going to represent our variables. So let's let X represent the mass of 20% chocolate, and let's let Y represent the mass of 5% chocolate. Okay, we're going to set up a table and see if we can put some of these numbers in here to help us figure out, well, what's the equation going to be? So it just takes practice getting used to this, but let's first identify. Let's say that this 20% chocolate is the first type of chocolate trail mix we're dealing with, and this 5% chocolate, this is our second type of trail mix we're dealing with. Okay, so we're going to set up a chart representing our trail mix. So we have trail mix number 1, we have trail mix number 2, okay? And then let's look at some of the information we have here. So it says what mass of each type needs to be mixed to make 950 grams. So I'm just going to circle that because that's 950 grams. This is one of the things we're trying to figure out. So it needs to be mixed to make 950 grams, okay? So when we're talking about grams, we're talking about the amount of something or the weight of something. So it's similar to saying how many coins do we have, how much mass do we have. So we're going to have a column that represents just our total mass. Okay, and trail mix number 1 is represented by X. So how much X do we have? How much Y do we have? And then we're essentially working to make this third type of trail mix. So we're working to combine those things to come up with a new third type of trail mix. And the total of that is going to be 950. Okay, so that's what we're working to create here. All right, it says it's going to be 950 grams, and then it says it will have 10% chocolate pieces. I'm looking back up in our equation. So this is going to be our second equation we're kind of working with. One's going to help us figure out how much do we need to make 950 grams, but the second component of it is that 950 grams needs to be made up of 10% chocolate. So we're going to create a couple columns here that will show that to you. So first, let's, again, just in the table, create a column that tells us what percentage of each of these trail mixes is made up of chocolate. So what I mean by that is for trail mix number 1, what percentage of trail mix number 1 is chocolate? And if we look back at our definition of our variables, it says that X is represented by 20% chocolate. So that's what we're going to write down here, just so that we have it in a nice organized table. So if we write that as a decimal, 20% chocolate makes up the chocolate pieces in trail mix number 1. If we take a look at trail mix number 2, what percentage is made up of chocolate in trail mix number 2? Well, according to our variable there and in the problem, it's 5%. So we can write that there's 0.05% chocolate in that trail mix. Okay, and then finally, in our third type of chocolate trail mix, or just trail mix, what percentage is made up of chocolate? And again, this is where we are trying to make up 10% chocolate. So remember, from our equation, this third type of trail mix we're trying to make up is going to be 10% chocolate. So if we wanted to represent how much chocolate is going to be used in each of these types of trail mix to make the third trail mix, we're going to make a column for that. So the mass of each type of chocolate. Okay, so for trail mix number 1, we know that it's going to be 20% of trail mix number 1. So when we think of, we should be thinking multiplication. Trail mix number 2 is going to be 5% of that trail mix. And then trail mix number 3, if we think about, we're going to again do 10% of what the total mass is. So we're going to do 0.1 times 950, which is going to equal 95. Okay, so that helps us set up our two types of equation. We can just basically combine the information we've put in each of those columns, and that's going to represent our equations. So for equation number 1, okay, we have x plus y equals 950. And then in terms of the mix of each type, we have 0.2x plus 0.05y is going to equal 95. All right, and that's how you set it up using a table. We're going to try one more table. This one is going to involve time instead of percentages, but the process is the same. So Brian manages a manufacturing plant that makes softball and hardballs. Each hardball requires 1 minute on the stitching machine and 3 minutes on the covering machine. Each softball requires 2 minutes on each machine. If the stitching machine is available for only 100 minutes each day, and the ball covering machine is available for 3 hours each day, how many balls of each type can be made? All right, so the question right there at the end says how many balls. So that's the unknown. That's what we're trying to figure out. So we're going to be looking at hard balls and soft balls. So let's let a variable represent those things. So we'll let H represent hard balls, and we will let S represent soft balls. Okay, a couple things to think about here, just like above. What are the things we're essentially trying to work with here? We have hard balls and we have soft balls. Then they do mention these machines that are used to make them. We have so much time on a covering machine and on a stitching machine. So those are going to be the things that represent the headings of our titles and our columns. And then we're going to have some totals that we need to work with. But let's first set up our table. Let's say that we're going to have softballs, and we're going to have hard balls. Okay, and then let's also say that we're going to have a stitching machine. And we will have a covering machine. And let's just make a table with those as our columns and the types of balls as our rows. So now we'll try to pull out the time required on each type of machine for these different type of balls, and that will hopefully help us set up an equation because we have some time constraints for how much minutes each day each of these machines are available. So it says each hard ball requires 1 minute on the stitching machine and then 3 minutes on the covering machine. So let's write that information down. So a hard ball gets 1 minute on the stitching machine and 3 minutes on the covering machine. Each softball requires 2 minutes on each machine. So 2 and 2. So 2 minutes on the stitching machine, 2 minutes on the covering machine. Okay, we're going to add in a third column because it gives us another restriction if we continue reading. It says if the stitching machine is available for only 100 minutes each day and the ball covering machine is available for 3 hours each day, how many balls of each type can be made? So let's add another column here just for our total time. All right, so it says if the stitching machine is available for 100 minutes each day. So let's put that as our total time. And I'm going to change that so just we're using the same color. So 100 minutes each day. Okay, and the ball covering machine is available for 3 hours each day. Well, we need to make sure that we're writing in the same units of time. So 3 hours is 180 minutes. So that's what we'll write for our covering machine. Okay. Now we have some equations we can deal with. We have no variables in our table, so we have to make sure we include those when we set up our equations. So it says how many balls of each type can be made. Okay, for equation 1, we know that we have 100 minutes total. So however many softballs plus however many hard balls we make on that stitching machine can't go past 100 minutes. So again, we're going to have to apply how much time each of those require. So we need 2 minutes for every softball. Okay, I'm looking at this column here. Plus we need 1 minute for every hard ball. And the total time there has to equal 100. We can do the same thing now for the covering machine. Okay, for the covering machine we need 2 minutes again for every softball, but we need 3 minutes for each hard ball. And this machine is only available for 180 minutes a day. So it has to equal 180. Right, so just a little bit different of a mixture problem where we're using time instead of percentages, but we will continue looking at these equations on the next day's lesson to then try to solve them using substitution and elimination. That is it for today's lesson.